half a lecture on Tuesday and the other half on Thursday. But we're doing fine. Okay, DC measurement instruments. I'm going to try not to read everything to you. Understanding the functional design and operation of electrical measuring equipment is important since they're used in repairing, maintaining, and troubleshooting electrical circuits. The best and most expensive measuring equipment is of no use unless the technician knows what is being measured and what each reading indicates. That's why most of these exercises in the lab have you do the calculations first and then measure with the meter. So that way you've got a little idea in your head what's going on. It's also helpful to know what you should be seeing on the meter. We'll just start. Meters are either self-excited or externally excited. Those that are self-excited operate from a power source within the meter. Externally excited meters get their power source from the circuitry that they're connected to. So digital meters, I think for the most part, all work off their internal battery. The Simpson does both. It uses whatever you're measuring to drive the meter, except when you're doing ohms, when you're doing resistance. And that's why I ask you to make sure that the meter is selected out of ohms when you put it away. So it uses the battery inside, the 9-volt battery, to use that. It pushes that 9 volts through your resistor to get a reading. So that's an example when it is self-excited. Externally excited is when we plug it into the wall to read voltage or we hook it to the batteries. It's using that battery source to drive the meter, to drive the needle. Bless you. So here's the Darson-Vahl meter movement, the basic DC type meter movement, first employed by a French scientist, Darson-Vahl, and you won't be tested on it in making electrical measurement, is a current measuring device which is used in the ammeter, voltmeter, ohmmeter. The pointer is deflected in proportion to the amount of current through the coil, and that's this coil right here. So there it is. The meter movement that has 1 milliamp sensitivity indicates that a meter movement will require 1 milliamp of current to move the needle to full scale. Likewise, a half scale deflection will require only a half milliamp of current. So no matter what we're measuring, if it's ohms, AC, DC, we're measuring current, this little meter, this little coil here is getting no more than a milliamp of DC current. So we're converting it inside the Simpson meter, no matter what we're measuring. In a standard meter movement may have a current sensitivity of 1 milliamp and a resistance of 50 ohms. If the meter is going to be used to measure more than a milliamp, then additional circuitry will be required to accomplish the task. This additional circuitry is a simple shunt resistor. We just started. So the purpose of the shunt resistor is to bypass current that exceeds the 1 milliamp limitation of the meter movement. To illustrate this, assume that the 1 milliamp meter in question is needed to measure 10 milliamps. The shunt resistor should carry 9 milliamps while the remaining 1 milliamp is allowed to pass through the meter.
Oh.
That's the shunt resistor.
It stops 9 millimeters?
It separates it out. And I've got a diagram that will show you. So again, that little coil will only see 1 milliamp of DC power, no matter what you're measuring. It shunts or scoots the extra off around. We'll see more of that. This I'm just going by the order of the book. Dampening to make the meter readings quickly and accurately. It's desirable that the moving pointer overshoot its proper position only a small amount and come to rest after not more than 2 small oscillations. The term dampening is applied to methods used to bring the pointer to an electrical meter to rest after it has been set in motion. Dampening may be accomplished by electrical means, by mechanical means, or by a combination of both. So this is a light vein. It's mechanical and it's a closed air chamber. It's just got a screen in there. So the air has to move through that resistive screen that keeps it from just bouncing all over the place. It gives a little more smoother action. The multi-range meter. So the basic idea of a multi-range meter is to make the meter usable over a wide range. In order to accomplish this, each range must utilize a different shunt resistance. So to give you an example of a 1 milliamp movement, 1 milliamp to move the meter full swing, we have our positive lead and our negative lead, and we have, this example has two switch positions, a 10 milliamp and a 100 milliamp. So here they're using a resistor. These are smaller, lower voltages. So 10 milliamps would be the max range that you would apply to this meter with it in this position. You could go as 100 milliamps. This is not shunting, but this is lower voltages, so it's reduced. There's a lot of different ways inside the meter that we make sure that this coil on that needle only sees that 1 milliamp of current. So that's that selector on the front of this doing is we're redirecting the flow of electricity and current. So
So would it shunt 9? Is that what it's?
you know, it's going to depend on the meter. This would be like down to the milliamps, where all we need is a resistor, and it's going to give us a ratio. If we were to literally measure, if there was a 1 milliamp setting, then it would just be direct. There would be no shunting, no resistance. But these 10 milliamp and 100 milliamp, they're smaller, so we do it with just a resistor. When the currents start getting higher, then we start shunting.
Shunting will go.
Yes. The voltmeter uses the same type of meter movement as the ammeter, but employs a different. Okay, so that's the difference, and I'm to stand corrected.
Yeah.
When you're measuring volts, it's going to use a resistor because you don't have the current flow. It's easier to drop the voltage and the current down when you're just measuring voltage. Its current is when you've got to do shunting.
Yeah.
If you remember, we put the current in series, and we need to be able to the circuit to still get the same amount of current. So we shunt when we do that.
Because it requires ampere 1.
Yeah, you've got to have flow through the meter. The voltmeter uses the same type of meter movement as the ammeter, but employs a different circuit external to the meter movement. So this is the resistor. That must be the resistor movement.
Yes.
That one doesn't necessarily show us that much. When voltmeters are used, they're connected in parallel with the circuit. And that's sometimes a question of yours. When you are measuring voltage, you are parallel. So if I've got, here's a parallel circuit, and if my battery came off to the side, that's my battery, it's a quick draw on the battery, the meter would be placed parallel alongside. These resistors are parallel already, so if I were to put a voltmeter in here, it would be wired essentially the same way. One connection on the positive side and a connection on the negative side. Even if I remove it out here, it's essentially parallel to the power supply.
There was a little confusion when I was reading. I talked to you last night about it. It says in the notes on the lab not to connect the meter to the power source.
Yeah.
But what we were doing is just connecting one lead to the power source.
Yes.
And as
So
long as you just connected one and not both, then
trying to think of how that would. I can't think of a. So the ammeter. You're measuring current with the ammeter, obviously.
Yeah.
So if I have a battery here, I'm going to put the meter in series. So everything flows through it. And I'm going to put a light here. This is my light. That's a basic almost diagram for a light. The light is going to restrict the flow. The light, I can plug that directly to a battery, and it's only going to take what it needs. And if it's a small bulb, this could be a huge, massive battery. An example like the lights on the dash of your car. the battery in your car has a lot of current in it. But those little lights are small and they just glow dimly. So they're only taking what they need from that battery. So when I put the meter in here, the bulb is what's controlling the amount of current. The meter is just measuring it. If I take the battery out and I connect that straight to the power source, now I'm unrestricted and I'm going to do damage to my ammeter. And that's what they were telling you in the notes. Don't hook it directly to the power supply. So if it's part of a working circuit, our ammeter is going to be safe. Okay, so that's what it means when we're parallel, when we're taking voltage measurements. When we are measuring current, we hook up the ammeter in series. If unsure about the voltage to be measured, take the first reading in the high value on the meter. And that's always a good idea. You want to check and recheck your connections before you make the final connection. You also want to just tap with the Simpson meter. Just tap it to make sure that the needle goes the correct direction instead of dragging it the wrong way. Also, the little fuses, what they're saying is if you don't quite know what you're going to read, set the meter at its highest level and then start coming down. So if I was going to measure the voltage in the wall and I didn't know how much was there, I would set it at 1,000 volts or 500 volts, whatever I knew was higher than what I was going to measure. And then I can get a reading and a feel and I can start dialing it down to get a little more accurate. Those little fuses in those multimeters, I was thought, they always give me a hard time when my class blows fuses. And I thought, I'll just buy, 50 or 60 bulk. I found out that I think the cheapest I could find was $3.20 a piece. So
In which one?
those are the digital meter, that little tiny glass fuse. In fact, I've got the case right here. I was going to stop by. I was on.
Looking at Amazon?
I did, and the prices range wildly. But the closest I found, I think I could get it down to $1.30 if I bought 1,000 of them.
Yeah.
So don't do that to me. So now I know why they always get mad at me when I keep asking for more fuses.
What size are they?
It's a
How many amps you get?
it's a GB. It says GDB first. I think that's designates as a smaller glass one, and it's a 315 milliamp.
Oh, yeah.
Because this is what this is doing. The 315 is protecting the measuring device. So essentially, back here is this 50 amp, 1 kilo ohm. They're putting the fuse here. So if you drive more power into this meter, you'll protect the meter. But then you prevent that from getting to that fuse in that meter by making appropriate selections on the front of the meter. So when those of you who have popped the breaker on the Simpson where it pops up, it goes click, it pops up. What it's done is it's just protected you from slamming that little tiny 1 milliamp needle with more current than it wants to see.
Save you $3.
Oh well, it's more than $3 if you cook that little Darson Vol meter. Okay, if the voltmeter has, and then again, make sure you turn them off resistance. That saves batteries. So if the voltmeter has the low resistance, it will draw off a significant meter of the current. So the meter's using power to drive that little needle. So the meter has resistance, and it will take power from your circuit.
Mauser has them for $1.43.
At how many minimum purchase?
One, if you want to buy 1,000, you get them for 65 cents each.
Okay,
You got it.
that wasn't Amazon, was it?
No, this is Mauser.
Okay.
Still.
First place I
I
looked.
saw-
Buy a truckload.
Go for the 1,000.
So $1.20, $1 what?
So if you buy, let's say 100, you get 100, you can get for 80.896 cents each.
Yes.
Maybe what I should do is have
We're gonna get the
Everyone-
bookstore to buy it.
Everyone donate?
everybody, if you blow a fuse, you gotta pay for it.
I thought you made $270 million.
Yeah.
That's what it goes for.
Okay.
570 can ship immediately.
Okay.
Immediately.
Well,
Right
so
now.
I'll have to look at that one. Cause I would rather spend
Tonight.
$40 out of my own pocket to give me a, you know, a little,
Peace of mind.
yeah, well, peace of mind or a little peace and quiet from,
Think.
you know, cause it reflects on me, cause that tells me I'm not preparing you to operate the meter correctly. And this is something that probably should be moved up to the front of the class instead of throwing you meters and start telling you measurements.
There you go.
Okay, so if the meter actually is taking power to function itself, it'll lower the effective resistance of the circuit and change the voltage readings. When making a voltage measurement, use a high resistance voltmeter to prevent shunting of the circuit. So a higher resistance is going to minimize how much it takes away. We're gonna have to do this in the lab. You're gonna actually go find out how efficient, how much the meter is shunting off. There's a formula for it. I hope I remember how it goes. I think I do. Okay, the ohm meter. The meter movement is used for the ammeter, and the voltmeter can also be used for the ohm meter. The function of the ohm meter is to measure resistance. The figure shows that the basic ohm meter contains a battery and a variable resistor in series to the movement. So that variable resistor in series is our rheostat. That's our zero dial. So we put a 9-volt battery in this. If that 9-volt battery always stayed 9 volts, we wouldn't need that zero. But as that meter starts to die, or that battery starts to die, we use that rheostat to re-zero it. So it might be 7.5 volts, but now we've adjusted the rheostat to where zero resistance is full scale. So full scale at 9 volts, and as that battery starts to die, the needle will start to drop. So we lower the resistance, and we allow that 7 volts more current from that 7 volts, because it only takes 1 milliamp. That 9 volts more than enough power to power that needle. But we need to, so we open up the floodgates a little more when the battery gets low. That's it for that.
Because it's either plus or minus, I don't think resistance until